Welcome back to the video course on fluid mechanics. We were discussing about the laminar and turbulent flow chapter. So, in the laminar flow, we were discussing about the how to say develop the various fundamental equations, and then we were discussing the flow over a flow through between two parallel plates, and then we were discussing about the flow when one of the parallel plate is moving, that means Q-tape flow, and then we were discussing about the pipe flow. So, with respect to the pipe flow, we have seen the basic equations, Hagen-Poiseuille flow equations we have seen. So, now say what we are doing here is, say we are trying to find out with respect to the basic principles, say Newton's second law, we are trying to get the basic equations for the velocity distribution, and then pressure distribution, and then the discharge through the pipe, and then shear distribution, and various other parameters. So, we have seen that here say the basic pipe flow is concerned, we can just describe say the flow with respect to the laminar flow in pipes. Say we are now concerned steady laminar flow through circular tube, and we have derived the basic equations for the say pipe flow from the fundamental principles, and then we have seen the expression for the velocity, the maximum velocity, and the discharge. So, now say further before going to the further topics on pipe flow. So, we will continue with the what we are discussing in the last lecture. So, we have derived the equations for the say the velocity variation as u is equal to minus 1 by 4 mu dp by dx into r0 square minus r square, where as described in the slide. So, here you can see say the radius of the pipe is r0, and then q is the discharge, and then we consider a fluid element like this. Using this concept only, we have derived the basic equation for the velocity in a pipe flow from the fundamental principle. So, u is equal to minus 1 by 4 mu dp by dx into r0 square minus r square, where r0 is the radius of the pipe, p is the pressure, mu is the coefficient of dynamic viscosity. So, for maximum velocity, we have seen that the equation is u max is equal to minus 1 by 4 mu dp by dx into r0 square, and then we have derived the equation for discharge. So, discharge we have integrated from 0 to r0 the radius, and then 2 pi r u dr, that gives the discharge as minus is equal to 1 by 8 mu into minus dp by dx into pi r0 to the power 4, and if you express minus dp by dx as del p by l, then we got the discharge as q is equal to pi d to the power 4 delta p by 128 mu into L. So, where d is the diameter of the pipe, delta p is the pressure difference, L is the length of the pipe, and mu is the coefficient of dynamic viscosity. So, this equation is called Hagen-Poiseuille equation for pipe flow. So, now say if you want to find out the average velocity, then the discharge is known, then we can just find the area of cross section of the pipe, and then discharge divided by area of cross section gives the average velocity through the pipe, and then we already got as v is equal to delta p into r0 square by 8 mu l by taking q by divided by pi r0 to the r0 square, and then if you want to find out the pressure at various locations of the pipe, then delta p is equal to 8 mu VL by r0 square, that is equal to 32 mu VL by d square. And here the energy loss per unit weight of fluid in laminar flow through a circular tube or pipe, we can write as delta p by gamma, that is equal to 32 mu VL by rho g d square. So, say now say we want to, if you compare, say now we are generally using the Darcy's-Weisbach equation for the loss in head loss due to friction and other factors in the pipe flow. So, if you compare with the commonly used Darcy's-Weisbach equation, which we will be discussing when we discuss about the pipe flow. So, the when we compare this equation which we derived here, delta P by gamma in the previous slide, delta P by gamma is equal to 32 mu L by rho g d square. If we compare this with the Darcy's Weisbach equation, then we can write this delta P by gamma is equal to 64 rho v d by mu into L by d into v square by 2 g. So, this Darcy's Weisbach equation is given as f L v square by 2 g d, where f is the friction coefficient for the pipe and L is the length of the pipe, d is the diameter, v is the average velocity, g is the acceleration due to gravity. So, therefore, we can write f is equal to the friction coefficient f is equal to 64 divided by rho v d by mu, that is equal to 64 by R e, where R is the Reynolds number. So, in comparison with the Darcy's Weisbach equation, the Hagen-Poiseuille equation which we derived here, we can write with respect to this friction factor can be expressed as 64 by Reynolds number for the case of pipe flow, for the case of laminar flow which we discussed now. So, now say sometimes the pipe can be, so the case which we have discussed is the pipe flow in horizontal position. So, sometime the pipe flow can be, say what we discussed here is, say when the pipe is horizontal in position. So, sometimes the pipe can be inclined. So, when we consider the inclined pipe, then we have to consider this angle theta, and then we have to consider the weight of the pipe or the gravity effect on the pipe. So, we instead when the pipe is horizontal is the what the equation which you derived earlier. So, for inclined pipe, when the pipe is, so you can see here, when this, if we consider this as a pipe, then this is the horizontal position, then we do not have to consider the gravitational effect or the with respect to the weight of the fluid. So, but when the inclination comes, we have to consider the gravitational effect here. So, with respect to the weight of the fluid. So, for inclined pipe, additional gravity force component to be considered here. So, pressure term is changed to P plus gamma Z. So, therefore, we can write the velocity u is equal to. So, here in our earlier expression for u, we got this u is equal to 1 by 4 mu dp by dx r0 square minus r square. This minus sign will be there depending upon dp by dx is negative or positive. So, in this case, when we consider the inclined pipe, we have to consider the additional gravity force component as we have seen. So, that means the horizontal pipe, and when the pipe is inclined, we have to consider the additional gravity force, and this we can here this we can consider by changing the pressure term P. We will change P to P plus gamma Z. That means the additional gravity force will be considered. P will be, now for inclined pipe, P will be equal to P plus gamma Z. So, therefore, the velocity can be written as 1 by 4 mu d by dx of P plus gamma Z into r0 square minus r square, where r0 is the radius of the pipe and small r is the at any distance from the center of the pipe. So, this way for inclined pipe we can modify the earlier equation for the velocity. So, in this equation we can find out the velocity variation at various locations of the pipe. So, with similar way the discharge equation and all other equation we can modify in the case of inclined pipe. So, as we have seen the dp by dx term, the pressure term will be changing to P plus gamma Z. So, the discharge term here we can just rewrite our earlier equation like this: Q is equal to 1 by 8 mu minus d by dx of P plus gamma Z into pi into r0 to the power 4. So, here you can see our earlier equation is here for Q. So, this is our Q equation. So, now this is modified as, say, Q is equal to 1 by 8 mu minus d by dx of P plus gamma Z into pi into r0 to the power 4, where r0 is the radius of the pipe. So, here this negative or positive for the pressure comes depending upon the direction of the flow which we consider. So, that is will be taken care with respect to the flow direction. So, like this for we can calculate various parameters for the inclined pipes. So, finally, as far as pipe flow is concerned now, if you consider, so we have seen that the velocity is varying. So, if you consider for pipe flow, say for example, say here the say if you consider the pipe like this here, then you can see that the at the center we always expect the maximum velocity, and then the velocity is varying, say with respect to parabolic variation. So, due to the no slip condition on the pipe boundaries, there will be the velocity will be 0 on the pipe wall, and then you can see that the pipe velocity will be maximum at the center, and then again say other side it will be 0. So, with respect to this we can now plot the velocity variation for the laminar flow in pipes. We can just here in this slide you can see that the velocity is varying, the velocity variation is plotted here. So, here it is 0 and then it is going to the maximum at the center line, and then it is coming back to 0 the other side of the pipe. So, this is the velocity variation the pipe. So, maximum velocity is at the center line. So, similar way we have already seen earlier the expression for the shear stress at the pipe wall. So, shear stress equation is here. So, if you find out the shear stress variation as far as pipe flow is concerned, here you can see the shear stress is same here will be 0 at the center line where the velocity is maximum, and then it will be the shear stress will be maximum on the pipe wall, and it will be a linear variation. So, the for pipe case laminar flow in pipes you can see that the velocity will be minimum on the pipe 0 at the pipe wall and maximum at the center line, and shear stress is concerned you can see that shear stress will be 0 on the center line of the pipe, and it will be maximum on the pipe wall. So, the variation we can find out from the earlier equation which we have derived in the case of velocity as well as the shear stress. So, now this pipe case, for the pipe case for laminar flow we have find out the various parameters, pressure variation, then shear stress variation, velocity variation and discharge variation. So, before closing this section on laminar flow, say we will consider one more special case where the case is called annulus. So, you can see that in many, especially in mechanical engineering and many other engineering cases, say this annulus is a say especially for many kinds of machines we use. So, here there will be one axial, or say the flow is between two sections like this. So, here is coming like this. So, now so here you can see, so the flow is between two, say one central axial and then with the pipe between the space of another pipe. So, we want to find out here the velocity variation, the pressure variation or the discharge and shear stress and all other parameter in the case of annulus. So, the case is a steady laminar flow through space between two concentric cylinders. So, here we consider this is the first cylinder and the second cylinder is here. So, we want to find out the various parameters for this annulus case, laminar flow in annulus case. So, the analysis is for velocity, shear and discharge. So, here also we are using the fundamental principles, that means Newton's second law. Here we consider fluid element, and then we consider say it's the forces acting on that, and now since it is steady state case we consider we will be equating the forces acting on the fluid element to 0, and then we will be finding out the various parameters as we did in the case of laminar flow in pipes, which we discussed earlier. So, if we consider a horizontal annulus of outer radius r1 and inner radius r2, then here we will be deriving the equation for velocity and discharge and other parameters. So, the fluid element of at r of size dx into dr here we consider. So, here this shows the figure. So, this is the inner cylinder and this is the outer cylinder, and the flow is between these two cylinder. So, the flow is direction is like this and then to derive an expression for the velocity variation and discharge and other parameters, here we consider a fluid element like this at a distance r from the center line, and the length of the fluid element is dx, and then you can see that the size dx by dr is considered, and the forces acting here are the pressure force and shear force. So, you can see that since it is under steady state condition, so here the forces acting are, first one is the pressure force. So, here P into 2 pi r dr on this side, and this side of the fluid element P plus dP by dx into 2 pi r dr, and then shear is concerned here tau into 2 pi r dx on this side if we consider, and if it here on this side it will be 2 pi into r plus dr into tau plus d tau by dr into dr dx. So, this is the fluid element which we consider, and the forces acting are the pressure force on both sides of the fluid element, and then the shear force. So, on this side given by tau into 2 pi r dx, and then with respect to the incremental other side it is 2 pi into r plus dr into tau plus dr by dr into dx. So, now with respect to this we will be considering the Newton's second law to derive the equation. So, from the Newton's second law of motion in the direction of flow, we can write P into 2 pi r dr minus P plus dP by dx into dx plus into 2 pi r dr minus 2 pi into r plus dr into tau plus d tau by dr into dx plus tau into 2 pi r dx is equal to 0. So, all the forces we equate to say the algebraic sum we equate to 0, and then if you divide by volume of the element, here this 2 pi r dr dx, and if you drop the infinitesimal terms and simplify this equation, the basic equation for this flow through annulus, laminar flow through annulus, we can write dP by dx plus d tau by dr plus tau by r is equal to 0. So, this is after simplification of the after application of Newton's second law, equating all the forces to 0, and then after simplification we get dP by dx plus d tau by dr plus tau by r is equal to 0. And now here to make our aim is to get an expression for velocity. So, now P is dependent on x and shear stress on r. This equation, the earlier equation, we can write as dP by dx plus 1 by r into d tau r by dr. So, this equation we can write in this form, dP by dx plus 1 by r d tau r by dr is equal to 0. So, this we can integrate with respect to r to get an expression. So, if we integrate this dP by dx integral r dr plus integral d by dr tau into r into dr is equal to a, where a is a constant. So, if we integrate this, here we have to put a constant a, and now this we can write to integration, we can write r square by 2 into dP by dx plus tau into r is equal to a. So, now this constant a we have to find out from the various boundary conditions for this particular problem. So, now here we substitute, here tau is equal to minus mu into du by dr, since here this minus symbol is used since the shear stress is say increasing in the direction of the pipe wall. So, that is why tau is equal to minus mu by du by dr is used here, and then here therefore, the laminar flow in the annulus we can finally write as dP by dx into r square by 2 minus mu into du by dr into r is equal to a, or dP by dx into r by 2 is equal to minus mu into du by dr is equal to a by r. So, now say if we again this expression, say our aim is to find out the velocity variation. So, now we got an expression with respect to the pressure gradient and the velocity gradient. So, final aim is to get an expression for velocity. So, we will integrate with respect to r once again. So, that will give dP by dx into r square by 4 minus mu into u is equal to a log r natural log r plus b, where b is another constant. So, now say the final equation is dP by dx into r square by 4 minus mu u is equal to a log to natural log r plus b, where a and b are constants. So, this a and b constants we can just find from this boundary condition. So, here you can see that due to the no slip boundary condition, say here there is the pipe wall, here the inner cylinder wall, here the inner cylinder wall, and here also at inner cylinder wall. So, here you can see that when the radius is r2, that means on this face here the velocity is 0 and here again the velocity is 0. So, similar way if you plot the velocity variation here at r is equal to r2, the velocity is 0, at r is equal to r1, the velocity is again 0. So, the velocity variation is parabolic between the cylinders. So, these boundary conditions we can apply here to find out the constants a and b. So, at r is equal to r1, u is equal to 0, and at r is equal to r2, u is equal to 0, from which we can find out the constants a and b. So, if you substitute this for once you can substitute here and then you can find out a and b, and then we can put back to get an expression for the velocity. So, these mathematical steps can be done here, and now finally, we can write the velocity expression as u is equal to minus 1 by 4 mu dp by dx into r1 square minus r square plus r1 square minus r2 square divided by natural log r2 by r1 into natural log r1 by r. The small r is the distance at which we will be finding the velocity, and r2 is the, as shown in this figure here, r2 is the inner radius of the cylinder, inner cylinder, r1 is the outer radius, and r is the distance at which we are finding out the velocity here. So, the final expression is u is equal to minus 1 by 4 mu dp by dx into r1 square minus r square plus r1 square minus r2 square divided by natural log r2 by r1 and natural log r1 by r. So, now once the velocity is found, as we did in the earlier case for the pipe flow, we can just find out the discharge passing through this the annulus between the two cylinders. So, just we can integrate q is equal to integral r2 to r1 2 pi r dru. So, this integration will give q the discharge flowing through the annulus. So, q is equal to integral r2 to r1 2 pi r dru, that is equal to minus pi by 8 mu into dp by dx into r1 to the power 4 minus r to the power 4 minus r1 square minus r2 square whole square divided by natural log r2 by r1. So, this gives the discharge, and then other parameters like shear stress, then pressure variation, all other parameters we can find as we are done in the previous case for the pipe flow. So, this once the velocity is known, we can find out the velocity gradient that you give with respect to that from the Newton's law of viscosity, we get the shear stress variation, and then with respect to the velocity variation also we can find out the pressure variation, since that includes the velocity expression, the expression for velocity includes the pressure variation. So, from which we can find out the pressure variation for the laminar flow in annulus. So, all other parameters once we find the velocity we can determine. So, the velocity gradient here du by dr is equal to minus 1 by 4 mu dp by dx into minus 2r plus r1 square minus r2 square divided by natural log r2 by r1 into minus 1 by r, and then shear stress is obtained as I mentioned using Newton's law of viscosity, tau is equal to minus mu du by dr, that gives 1 by 4 mu for 1 by 4 minus del dp by dx into 2r plus r1 square minus r2 square divided by natural log r2 by r1 into 1 by r. So, this gives the shear stress. So, now as we have plotted the velocity variation in the case of pipe flow, here also we can plot the velocity variation. So, as I mentioned, due to the no slip boundary conditions, so on the pipe wall as well as the inner cylinder wall, the velocity will be 0. So, you can see here I have plotted the velocity variation. So, here this location and this location, that means on the pipe wall. Here you can see both places the velocity is 0 and then it is going. So, here at this line it is the maximum velocity. So, this is the velocity u, and similarly below here also very similar way you can plot the velocity. So, here the minimum on both side and here the maximum velocity. So, very similar way we can plot the shear stress variation and we can find out all other parameters. So, these problems, this is a typical problem. So, very similar way we can solve most of the laminar flow problems by considering the first principle itself, that means the Newton's second law itself. We can derive various equations, various analytical expression or exact solution for simple laminar flow steady state condition. So, this way we can solve the laminar flow conditions. So, further this laminar flow problems we will be discussing when we go to the chapter on Navier-Stokes equation. So, Navier-Stokes equation also can be used for the to find out the laminar flow conditions by solving the Navier-Stokes equation, that we will be discussing later. So, in this chapter now, since we have covered the fundamentals of the laminar flow, say first we consider the laminar flow between two parallel plates and various other problems with respect to the parallel plates. Now, we have considered the pipe flow. So, the next section in this chapter is we are going to consider the turbulent flow. So, for turbulent flow, say as we have discussed earlier, the flow in nature can be laminar or say in transitional stage or in turbulent condition. So, here you can see that say if you consider the flow through a pipe, here you can see that say if you put a filament of dye with respect to through a pipe, then say the flow is as we have already seen, there is no disturbance to the flow and the flow is in layers, and so that is a laminar flow. And then when we increase the velocity of the pipe flow, you can see that and there is a lot of disturbance takes place and then a transition stage comes, and then finally if you increase the velocity, then you can see that the flow become turbulent. So, this is the laminar flow and turbulent flow which we have discussed in the beginning of this chapter. So, now we are going to discuss more on the turbulent flow as we have already covered the laminar flow at steady state. So, now we will be discussing the turbulent flow. So, the flow, the laminar to turbulent, so as we have seen, it is through a transition stage. So, naturally the flow, the laminar flow is calm, and so then you can see that it is mostly in layers. Say for example, if you go to say a river where the flow is just say the slope of the river bed is small and then there is not much disturbance, you can see that flow is very slow and then it is can easily observe, and then it is laminar in nature, it is very calm and quiet flow. But when say the river, say if the slope of the river changes at some place or due to some obstruction, like say big stone or something is there, then you can see that this laminar flow itself start to mix and then initially transition takes place, and then you can easily observe that the flow become turbulent. So, here in this slide you can see that how this phenomena takes place. So, laminar to turbulent flow through transition. So, you can see that here the flow is laminar, here the flow, this is in the flow is in layers, and then if you put as we have already seen, if you inject dye or a tracer, you can see that since the flow is also laminar, the dye is also moving in layers like this. Then you can see that if the turbulence conditions, say if the condition is going to the turbulent, then you can see that there is a lot of mixing takes place, and then initially this region is, say we can say transition, and then between the layers a lot of intermixing takes place, and then say flow disturbance takes place, and then finally the flow become turbulent. So, here you can see that here this trace of the tracer or dye is here say layer or undisturbed here, but then slowly the disturbance starts in the transition stage, and then you can see that a lot of disturbance. When the flow become fully turbulent, then the dye also you can see that it is totally mixing between, and then all the flow, the molecules change from one layer to another, and then a lot of disturbance takes place, and finally the flow become turbulent. So, you can easily observe this in nature. As I mentioned, if you go to a river and say if there is suddenly if there is a rainfall also, you can see that then lot of water comes and then the flow itself is disturbed. So, a number of examples we can place, we can see as far as how a laminar flow is transforming to a turbulent flow. So, now you can see here, say in this here, so you can see that the flow is initially coming as laminar. So, this is actually the gases or the pollutant gases coming out of a chimney or out of a pipe. You can see that initially it is, say here, depending upon various conditions, initially it is laminar, and then lot of mixing takes place, and then finally it become turbulent. So, here you can see the process of instability of flow system. So, what happens, the flow in the laminar flow, the flow is stable, and then for the turbulent flow lot of instability takes place to the flow system, and then what happens is erratic motion of fluid particles with a violent transverse interchange of momentum. So, this is what is happening. So, as far as turbulent flow is concerned, we can say that erratic motion of fluid particles with a violent transverse of interchange of momentum. So, this is the basic definition of turbulent flow. So, fluid, say in the laminar flow, the fluid is calm and quiet, and then it is in layers, and then in turbulent flow lot of erratic motion takes place, and then fluid particles, there is violent transverse interchange of momentum. So, this is the basic definition of turbulent flow as demonstrated in this figure, in this animation. And now, the turbulent flow, say as we have seen, turbulent flow is a flow regime characterized by low momentum diffusion, high momentum convection, and rapid variation of pressure and velocity in space and time. So, turbulent flow characteristics we can define like this: there is low momentum diffusion takes place, and then there is high momentum convection takes place, and then rapid variation of pressure is taking place between the flow, and then velocity also changes rapidly in space and time. Turbulent flow can be characterized. So, that means low momentum diffusion, high momentum convection, and then rapid variation of pressure and variation of velocity in space and time. So, here you can see that now submarine is moving in the sea, and then you can see that due to the speed of the vehicle here, the submarine, say you can see that lot of, say when the submarine starting position, it is laminar, there is not much disturbance, but when it started, and then you can see that lot of disturbance takes place, and then high momentum convection takes place, and pressure, rapid variation of the pressure takes place, and also you can see that velocity is changing drastically in space and time. So, this is the phenomena taking place as far as turbulent flow is concerned. So, now to further we can put, as I mentioned, we can put a number of examples for turbulence in nature, since many of the problems are turbulent type flow, say other than few of the, even normal pipe flow, when it is say the velocity, that means when you are opening the pipe slowly, then it is laminar, but after some time if you open completely, then you can see that the flow become turbulent. So, there are a number of examples we can put. So, here in this slide you can see that flow over a sphere. So, you can see the sphere is here, and then due to the various flow conditions, you can see that say this is actually an example of external flow. So, the free stream velocity is hitting on the sphere or cylinder, and then you can see a lot of mixing takes place, and then finally due to various conditions here the flow become turbulent. So, this is an example for a sphere, and as we have already seen, flow over a submarine. So, here you can see a submarine, and then how much turbulence are created. surrounding this. Actually, these figures are taken from this website as shown here, and then you can see say especially when a aeroplane is flying, the tip vortex from airplane wing, that also is a turbulent flow. So, like this we can have a number of examples turbulent flow, and this turbulent flow is very complex flow compared to laminar flow. Turbulent flow, as we can observe here in various examples, it is very complex flow. The analysis is very difficult. If you want to find out the velocity or pressure variation or shear stress variation distribution, then we have to do a very complex analysis as far as turbulent flow is concerned. So, this is a real challenge to the engineers and fluid mechanics scientists to deal with the turbulent flow. So, now further to see the examples of turbulent flow. So, when we in this slide you can see when we open a tap, as I mentioned, say it will pass through several stages as the tap is opened. So, for initially the tap is off, that means no flow, and then when the tap is slowly opened, you can see that when the tap is slowly opened as demonstrated here, then the dripping, the water is coming slowly as drips, and then it is called a dripping flow, and then slowly increasing, then you can see that the flow becomes laminar, then the continuous flow is there. Initially no flow, then dripping flow as drips, and then you can see that laminar flow is coming, continuous flow, and when if we increase the opening of the valve, then you can see that the flow become turbulent. So, this happens above a certain critical flow rate, that means say we can define in terms of Reynolds number as we have discussed in the initial part of this chapter. So, we can define with respect to certain critical flow rate. So, then the flow become laminar to turbulent through a transitional stage. So, water becomes in the turbulent flow, you can see here the water becomes unsteady and asymmetric as far as the turbulent flow is concerned. So, similar way, various way, when you are playing golf, you can see that when you are hitting the golf ball, then whatever, if you analyze the flow surrounding the ball, or when you are throwing a cricket ball, when you analyze the flow surrounding the ball, you can see that and the flow is totally turbulent. And then also, as we have seen, the smoke from a chimney also is turbulent. So, these are some of the important examples of turbulent flow which we have to analyze practically for various engineering problems. So, now before going to the fundamental equations of turbulent flow, we will initially see the various fundamental characteristics of turbulent flow, and then we will see how the various parameters variation is taking place, and then we will go to the derivation of the basic equations of turbulent flow. So, as we have seen, you can see here in this slide, for laminar flow the longitudinal pressure gradient, that means it is proportional to first power of velocity. So, if we consider the laminar flow, the longitudinal pressure gradient is proportional to the first power of velocity, as we have already seen, but you can see that turbulent flow is concerned due to the intermixing and then various variations of parameters. The pressure gradient is nearly, we can observe that it is nearly proportional to the square of mean velocity. So, this is what is happening in the laminar flow, the pressure gradient is proportional to the first power of velocity. In the case of turbulent flow, the pressure gradient is nearly proportional to the square of mean velocity, square of the mean velocity. And then other important character here is the shear layer is unstable. Due to the shear layer instability, most often this is actually the shear layer instability is the most often the responsible for turbulence. One of the major factor for creation of turbulence, the shear layer is unstable, and then this creates turbulence. So, now as we have seen in the preliminary section, we can preliminary discussion on this chapter, earlier discussion on the chapter, we can define with respect to the Reynolds number, we can define the turbulent flow. So, as we have seen in the famous Opson Reynolds experiment in 1883. So, Reynolds, what he did as shown in this slide, he put water in a say tank, and then a small tank he filled the dye, and then put in this form, and then he fitted a pipe here, and then with respect to the tank he put a valve here. So, as we can observe, when the valve is opening initially, so this is here you can see when the valve is opening, a filament of dye is passing through. So, the flow is very much laminar in nature. Then you can see that after some time, say the flow is in transition stage, when the valve opening is increased, then you can see small disturbance starts, and then it becomes finally totally turbulent. So, Osborne Reynolds is the first person who first studied how this can be classified, whether as flow is laminar, transitional or turbulent, and then he put forward the Reynolds number. As we have discussed, Reynolds number is the ratio of inertia force to viscous force, and we can generally define as rho v d by mu, where mu is the coefficient of dynamic viscosity, d is the diameter of pipe, v is the velocity, rho is the mass density, and depending upon the flow condition, this turbulence can be there in pipe flow, open channel flow. For any flow conditions, flow can be either laminar or in transition or turbulent flow. So, with respect to the Reynolds number, Osborne Reynolds classified the flow in pipe flow or open channel flow. So, as we know, when the flow is in open channel or pipe flow, the Reynolds number variation is say large variation will be there. So, he defined the turbulent flow. The pipe flow is concerned, the flow is said to be turbulent when the Reynolds number is larger than 4000. So, say you can say that the Reynolds number is less than 2000, as we have seen for pipe flow it is totally laminar. So, 2000 to 4000 it is actually in transition stage, and when the Reynolds number is exceeding 4000, we can definitely say that the turbulent flow is existing in the pipe, so or the pipe flow is turbulent. And similarly, in the channel flow is concerned, as we have discussed earlier, up to Reynolds number of 600 something, the flow is laminar for channel flow, and say up to 600 to 2000 it is transition stage, and then beyond 2000 the flow is in open channel flow, we can say that the flow is becoming turbulent. So, with respect to the Reynolds number, we have already seen how we are classifying the flow as laminar and turbulent. So, now we will see various factors affect the transition from laminar to turbulent. So, as we have observed in the experiments, or even we can observe when we are opening the tap with the valve of a pipe, then say flow is changing from laminar to turbulent. So, what are the factors that affect the transition? So, we will briefly discuss here what are the important factors that affect this transition from laminar to turbulent. So, some of the important parameters I have listed here. So, these are first one is free stream turbulence in incoming flow, that means initial turbulence. So, this free stream turbulence means the flow is already laminar, and then you are disturbing the flow. You can just say, for example, in a canal or in a river, the flow is flowing say in laminar calm and quiet condition, and when you are putting a big stone on in the river or in the canal, then you can see that due to the impact there is a lot of disturbance take place, and then stream turbulence takes place, and this incoming flow is initial turbulence. So, due to this the flow can become turbulence. So, this is a small example, it can become turbulence. And then second important factor is pressure gradient dP by dx. So, say when the pressure is say drastically changing, that means if pipe flow is there at one section the pressure is less, and at some other section the pressure is very large. So, you can see that there is the pressure gradient is very high. So, the pressure gradient dP by dx is very high. So, in that case the flow can change from laminar to turbulent. And then another important reason I have listed here is roughness of boundary. So, say for example, if say in a glass flume the flow is taking place as laminar, and then suddenly it changed to a flow, say wherever a concrete bed or wherever large number of stones are put, then you can see that there is the roughness, that means the roughness of the say wall or the bottom is changed. Say for example, here I will just draw, say here the flow is coming here, and then it is now laminar, the flow is going as laminar. So, here you can see that the bottom wall or the bottom is smooth, and then if it changes to, you can see that a small change here, that means the surface become rough, then you can see that lot of say due to the shearing effect, the shear stress increases, and then you can see that a small mixing starts here, and then the flow can, this laminar flow can become turbulent due to this reason. So, the third reason which I have listed here is the roughness of the boundary, and then the fourth reason can be curvature of boundary. So, if the flow is taking place in a smooth and then normal horizontal direction, and then sudden curvature is there. So, that you can see that in this case due to various parameters of the flow change, and then the laminar flow can become turbulent. And then another important factor I have listed here is suction of boundary layer. So, boundary layer, you can see that most of the cases boundary layer will be formed. Here you can see, say boundary layer formation can take place with respect to when the free stream flow is coming, and then if there is suction for this boundary layer, then also the flow can change from laminar to turbulent. So, the important here again I will just go through the important parameters. So, factors affect transition from laminar to turbulence. Important factors are, first one is free stream turbulence in incoming flow or the initial turbulence. The second one is the pressure gradient dP by dx. Third one is the roughness of boundary, and fourth one is the curvature of boundary, and fifth one is the suction of boundary. So, these are some of the important parameters. There are many other parameters also for some where the flow can change from laminar to turbulent. So, you can see here with respect to the various parameters which we discussed in the last slide. So, here you can see what are the causes of turbulence. So, what is finally happening is this figure shows what is happening. So, causes of turbulence we can just list into two major factors. So, first one is abrupt discontinuous velocity distribution. So, you can see here the flow is coming, and then due to various parameters, various factors, discontinuity takes place. You can see here this rock is here, and then the flow is coming, various obstructions are there, and then due to this the velocity become discontinuous, or discontinuous velocity distribution takes place. So, this can be one of the major cause of turbulence. And then another important factor, another important reason or cause of turbulence is shear flow. So, here you can see there is variation of mean velocity in space, and then shear flow takes place, and that can be another cause. So, these are two important causes of turbulence, and earlier we have seen 5 factors affect transition, and these are two important causes of turbulence. So, now say our problem now, as I mentioned, the turbulent flow is very complex in nature. So, laminar flow it is much easier to analyze. For turbulent flow it is very difficult to analyze. Then how to express the turbulent flow. So, generally you can see that if this is the flow, then say this, let us consider say mean flow or the laminar flow with respect to this, and then you can see that we can just superimpose say the variations like this. That means say the mean, we can consider a mean component of the velocity u bar, and then with respect to that mean component we can see what are the changes u dash or the transition takes place. So, this is where the way which we represent. So, the velocity of turbulence or turbulent flow velocity we can express u is equal to a mean flow component and then the instantaneous flow component u dash. So, this is the way generally we express the turbulent flow. So, here in this slide you can see. So, in 3 dimensions we will be having the flow x component, y component and z component. So, u v and w component. So, u is expressed as u bar plus u dash, where u bar is the mean velocity component, that is is equal to 1 by t, where t is time is a long time is considered. So, 1 by t integral 0 to t u dt, and v turbulent velocity in y direction v is equal to v bar plus v dash. So, where v bar is equal to 1 by t integral 0 to t v dt, and similarly w is equal to w bar plus w dash, where w bar is equal to 1 by t integral 0 to t w dt, where u dash, v dash, w dash are the instantaneous velocity with respect to mean velocity as we have discussed. So, this is the general way we describe the velocity variation in turbulent flow. So, there will be a mean velocity component, and then there will be an instantaneous velocity component, and then we will be adding together. So, that will give the velocity in x, y or z direction at appropriate time. So, this is the way we describe the velocity component. And then the time average of fluctuations, you can see that this u, v and w are, say, the fluctuations we consider for long time, then you can see that this will be, the fluctuations will be 0. Say for example, if you consider the mean value of the fluctuations u dash bar is equal to 1 by t integral 0 to t u dash dt. So, that can be expressed as 1 by t integral 0 to t u minus u bar dt, that is equal to u bar minus u bar. So, this is equal to 0. So, this way we can say that the time average fluctuations of the velocity components in turbulent flow is 0. So, therefore, u dash mean value is equal to v dash mean value is equal to w dash mean value is equal to 0. And then the root mean square of u dash, we can express, this will be the violence of turbulence fluctuations and measure of the intensity of turbulence. So, the intensity of turbulence or the violence of turbulence of fluctuations we can express as square root of u bar dash or square. So, this gives the violence of turbulence of fluctuations and measure of intensity of turbulence.